Welcome back to the deep dive. Today, we are crossing a very specific and I think very important threshold.
Hmm.
If you've been with us for the previous discussions on biochemistry, we've spent a lot of time acting like, I don't know, architects or maybe structural engineers.
Right. We've been looking at the blueprints.
Exactly. We've analyzed the bricks, the amino acids. We've marveled at the structures they can build. The alpha helices and the beta sheets. We've admired the static beauty of the molecule.
That's a perfect way to put it. We've built the machine. Up until now, we've essentially been walking around a car showroom admiring an engine block that's just sitting on a stand.
Oh, I like that.
We said, look at that chrome, look at the geometry of those pistons. It's beautiful, it's intricate, but it's fundamentally a statue. It's being, but it's not doing.
But today we turn the key. We are finally moving from structure to function. We're going from the abstract to the active.
We're starting the engine.
We are. And to help us navigate this transition, we are adopting a bit of a persona for this deep dive. We're putting on our deerstalker caps. We are becoming Medlock Holmes.
I love the detective angle. I really do. Because when you look at protein function, which is the title of the chapter in Leninger we're really digging into, you are investigating behavior.
It's not a static object anymore.
Not at all. You're no longer looking at a suspect in a lineup. You're watching how that suspect interacts with the world. Who does it talk to? Who does it, avoid? How does it react when it's under pressure? Does it have a temper?
And just like any good investigation, we need our case files. We are synthesizing insights from two absolute titans of the field.
The essentials.
First, we've got the rigorous physics and mechanics from Leninger's Principles of Biochemistry, specifically that chapter on protein function. I think of this as our manual on the physics of molecular intimacy. It tells us how the crime should go down, theoretically.
And then, to see what happens when the plan goes completely sideways, we have Harper's Illustrated Biochemistry. We're looking at the chapters on myoglobin and hemoglobin, and then plasma proteins and immunoglobulins.
So Harper is our clinical field guide.
Exactly. It grounds all that beautiful physics in the messy reality of the human body. It shows us the consequences.
Now, I want to make a disclaimer right up front here. We are going to go deep today. Probably deeper than we usually do. But please remember, this conversation is an interpretation. It's our synthesis.
Yes.
We are not just reading the textbook to you. If you are a medical student, a clinician, or just a hardcore enthusiast listening to this, you really need to read the source material. Please use this episode as your conceptual map. Think of it as a scaffold.
We're here to light up the path, but you actually have to walk it. The goal here is to give you those aha moments so that when you're staring at, say, a binding curve in the book, it doesn't look like abstract math.
It looks like a story?
It looks like a story. That's the whole point.
So let's start with the crime scene, or I guess the scene of the action. If we had to boil down everything a protein does, carrying oxygen, fighting a virus, moving a muscle, we had to get it down to one single unifying concept, one prime directive, what would that be?
It is, without a doubt, reversible binding.
Reversible binding. Okay, that sounds almost deceptively simple.
It sounds so basic, but it is the fundamental constraint of life. Just think about it for a second. Function in biochemistry is almost never a solo act. A protein just floating alone in a void, it does nothing. Function is a relationship.
A relationship.
It is a protein grabbing something, we call that target, a ligand, holding on to it just long enough to do a specific job, and then crucially, letting it go.
The letting go part, that's the part people forget, isn't it?
It is the most important part. It really is.
Yeah.
If a protein grabs a molecule and never lets it go, you don't have a functional machine. You have a paperweight. You have a rock.
Right. It's clogged.
It's clogged. And if it never grabs it at all, well, then you have a ghost. Life exists in that very narrow, very dynamic window of catch and release. The interaction has to be transient.
Okay, so let's unpack this catch and release. You use the word ligand. I just want to make sure everyone is on the same page. What actually qualifies as a ligand? Is it just small molecules?
No, it's an incredibly broad definition. A ligand is strictly defined as any molecule that is bound reversibly by a protein. That's it.
So it could be anything.
Anything. It could be a tiny oxygen molecule, O2. It could be a massive antibody protein binding to another protein. It could be a hormone like insulin or a drug you take. The key is that the bond is transient. It's a handshake, not a handcuff.
And Leninger makes a huge deal about the specific nature of this handshake. It's not just two things bumping into each other on the subway. It's purposeful.
Oh, it's highly specific. And this brings us to the binding site. You have to imagine a cleft or a pocket on the surface of the protein. And this pocket is complementary to the ligand in basically every possible way you can imagine.
When you say complementary, I think most people, myself included, immediately think of shapes, like a puzzle piece fitting into a hole.
And shape is the starting point, yes,
Yeah.
absolutely. If the ligand is round, the pocket is concave. But it goes so much deeper than that. It's complementary in size, in electrical charge, and in what we call hydrophobic character.
Meaning whether it likes or hates water.
Precisely. So if the ligand has a positive charge on it, the pocket will be lined with negatively charged amino acids, like aspartate or glutamate, to literally pull it in with an electrostatic attraction.
And if the ligand is greasy,
If the ligand is greasy and hates water, the pocket will be lined with other greasy hydrophobic amino acids like leucine or valine. It creates a little water-free zone to make the ligand feel right at home.
I remember in high school biology, and probably college too, seeing the lock and key model. You have this rigid keyhole, and only the one perfectly shaped key fits. It's such a classic image.
It is.
But the research, especially the way Leninger presents it, suggests that's a bit outdated, isn't it?
It is. The lock and key model, which Emil Fischer proposed way back in the 1890s, is a fantastic metaphor for specificity. It gets that part right, but it's terrible for function
Why?
because it assumes the protein is a rigid rock, a static keyhole. But we know now that proteins are incredibly dynamic. They breathe, they move, they flex.
So what's the better model?
The more accurate model, the one that really captures the dynamism, is induced fit.
Induced fit. Okay, walk us through that. What does that mean?
Okay, imagine a baseball catcher's mitt. When the mitt is empty, just sitting there, it has a general shape that looks like it could hold a ball, but it's kind of open, it's a bit loose.
Right.
The moment the baseball hits the leather, what does the catcher do?
The catcher clamps down. The mitt changes shape to wrap around the ball.
Exactly. The protein undergoes a conformational change. It actually moves. The protein structure shifts to hug the ligand tighter after that initial contact.
Oh, that's interesting. So it's not a preformed perfect fit.
No, the fit becomes perfect because of the binding. This allows for a much tighter interaction, but more importantly, it means the protein can be regulated. If it can move, you can control its movement.
So the protein isn't just a passive bucket waiting to be filled. It's actively reacting to the arrival of the ligand. It's a dynamic hug.
A dynamic hug is a great way to put it.
Now, we promised we'd decode the math of affinity without making everyone's eyes glaze over, but we have to do this because this math, specifically the dissociation constant, or θ-ED-DAL, this is the language of pharmacology. It's how we dose drugs. It's fundamental.
Right, and this is actually very, very intuitive if you don't let the notation scare you away. The θ-ED-DA is just a number, and that number tells us how sticky a protein is for its ligand. It quantifies the strength of that grip.
Okay, here's where I always get tripped up, and I know our listeners do too. In the textbook, it says a low DoD dollar means a high affinity. That feels completely backwards to me. If I have a high affinity for, I don't know, chocolate, shouldn't my number be high?
You would think so. It's
Yeah.
a very common point of confusion, but you have to look at what the number actually represents. T dollars is measured in molarity. It's a concentration.
Okay.
Specifically, it is the concentration of ligand you need to have floating around in the solution to fill up exactly half of the available parking spots on the protein.
Okay, let me try to visualize this. I've got a bucket full of proteins. Each one has a parking spot. I start sprinkling in ligands.
Correct. Now imagine your protein is super, super sticky like molecular superglue. It absolutely loves the ligand. Do you need to sprinkle in a lot of ligands to get them to find the proteins and stick?
No. If it's that sticky, the moment I drop just a few in, they'll latch on immediately, so I'd only need a tiny amount.
Exactly. You only need a tiny concentration, a low number. Therefore, a low dollars means the protein grabbed the ligand really easily. It implies high affinity.
Okay, that clicks. And the flip side would be,
The flip side is, if the protein is slippery, if it has low affinity and doesn't really care about the ligand, you have to flood the zone. You have to dump in a massive amount of ligand just to force them into the binding sites by sheer probability.
so you need a high concentration.
A high concentration, a high number. So a high key dollar means a loose grip or low affinity.
Low number, tight grip. High number, loose grip. Okay, I think I have it now. Give us a real-world benchmark from the text. What is considered ridiculously tight?
Well, the gold standard for a tight bond, the one Leninger always uses as the extreme example, is the interaction between a vitamin biotin and a protein called avidin.
Avidin. That's in egg whites, right?
Exactly. It's a defense protein in egg whites. It protects the egg by sequestering biotin so that invading bacteria can't use it to grow. And it binds biotin with a daily of roughly 1 times 10 to the minus 15th molar.
10 to the minus 15. That's effectively 0. It's an infinitesimal number.
It's as close to a permanent bond as you can get in biology. It's so tight that while it's technically reversible, for all practical purposes, it's permanent. It's like setting the ligand in concrete. Once avidin grabs biotin, it never lets go.
Which is perfect for an egg defense mechanism. You want to lock that stuff away. But that would be terrible for something like an enzyme that needs to do work.
Precisely. This is why context is everything. An enzyme needs to catch a substrate, chemically change it, and then throw it out so it can catch the next one. It needs to cycle thousands of times a second.
It needs to be a juggler.
It needs to be a juggler. If it held onto its substrate like avidin holds biotin, the enzyme would be clogged instantly. It would be a one-shot wonder, and then it's done.
So an enzyme would have a much higher acetary.
A much, much higher eigenolars, somewhere in the range of, say, 10 to the minus third to 10 to the minus 7th. A looser grip that allows for that rapid turnover.
So the math isn't just arbitrary, it really does describe the protein's personality. Is it a hoarder like avidin, or is it a fast-moving juggler like an enzyme?
That's a perfect way to put it. And we can visualize this personality with a graph. If you plot the concentration of ligand on the x-axis and the percentage of bound protein on the y-axis, you almost always get what's called a hyperbolic curve.
Right, it shoots up fast at the beginning and then it flattens out.
It shoots up fast as you add ligand, and then it levels off as all the binding sites, all those parking spots get taken. It reaches saturation.
Okay, so that's the fundamental physics of intimacy. We have ligands, we have induced fit, and we have the sticky math of T-day-D dollars. Now let's apply this to probably the most famous duo in all of biochemistry, the oxygen paradox. This is covered so well in Harper because it is the absolute basis of respiration.
The oxygen paradox is, at its heart, really simple. You are a big multicellular organism. You have thick tissues, muscles, a brain. You need oxygen everywhere, all the time, to burn glucose and make ATP.
The fuel of the cell.
The fuel of the cell.
Yeah.
But oxygen is terrible at traveling in your blood.
It's not soluble in water.
It's very poorly soluble. It's a nonpolar gas.
Yeah.
If you just had to rely on oxygen dissolving in your plasma the way sugar dissolves in tea, you would probably need a heart the size of a small car just to pump enough fluid to keep your brain alive.
So you can't just dissolve it. You need a carrier.
A truck. You need a truck. But here's the next problem, and Leninger points this out beautifully. Proteins are made of those 20 amino acids, and none of their side chains are any good at grabbing oxygen reversibly.
So the protein itself can't do the job.
Right. Carbon, nitrogen, sulfur. They just don't have the right chemistry for reversible oxygen binding. So biology had to outsource the job. It brought in a subcontractor, a transition metal.
Iron. The ferrous iron.
F+.
Iron. But as you know, iron is dangerous stuff.
It's extremely reactive.
Extremely. This is the whole Fenton chemistry problem. Free iron floating around in your body is incredibly toxic. It reacts with oxygen to form free radicals, specifically hydroxyl radicals, which are like molecular shrapnel. They just shred DNA, lipids, proteins, anything they touch. And it rusts, right? It oxidizes to Fe3 which can't bind oxygen anyway.
Exactly. So you're dealing with a toxic rusting metal that you absolutely need to transport the most vital gas for life. It seems like a terrible design choice.
It's high risk, high reward, I guess.
It is. And to make it work, to manage the risk, you have to build a cage for the iron. And that cage is the heme group.
Okay, what is heme exactly?
It's a complex organic ring structure. It's called a protoporphyrin ring, and it sequesters that iron atom right in the center. The heme acts like a bodyguard for the iron.
It keeps it from causing trouble.
It prevents the iron from bumping into things that would oxidize it to rust, but it leaves one very specific coordination bond, one angle, open for an oxygen molecule to slot in and bind.
And this heme group, this cage with the iron inside, is tucked inside our first protein of the day, myoglobin.
Myoglobin. This is our storage locker. It's found primarily in your muscle tissue, especially the red muscles like in your legs or your heart, the muscles that need to work hard for a long time.
And what's its personality? If myoglobin were a person, who would it be?
Myoglobin is a hoarder. It loves oxygen. It has a very, very low GGDR. If there is even a tiny bit of oxygen floating around, myoglobin snatches it up and holds onto it as tightly as it can.
Okay, which immediately creates a problem if you want to use it for transport across the whole body.
Exactly. Imagine a delivery truck that loads up with packages at the factory, drives to the supermarket, but then the driver refuses to open the back doors because he loves the cargo too much. That's myoglobin.
It's a failed delivery.
A failed delivery. And if you look at its binding curve in the textbook, it's a perfect hyperbola. It loads up instantly, even at very low oxygen pressures. So sure, we pick up oxygen in the lungs, no problem. But when it got to the tissues where you need to drop it off, it wouldn't let go. It would just drive right past and starve the tissue.
So myoglobin is great for a backup tank in the muscle, like an in case of emergency break glass supply, but it's terrible for system-wide delivery. Enter the main character, hemoglobin.
The delivery truck. Hemoglobin is a completely different beast. It's not a monomer like myoglobin. It's a tetramer.
4 subunits.
4 subunits.
So
2 alpha chains, 2 beta chains. You could think of it as 4 myoglobin-like proteins all stuck together. But because they are stuck together, because they can communicate, magic happens.
And this is where the binding curve changes dramatically. We go from that simple, steep, hyperbolic curve of myoglobin to the famous sigmoidal curve of hemoglobin, the S shape.
That S shape is probably the single most important line in all of physiology. I'm not exaggerating. It means that hemoglobin has a split personality.
Oh, so.
In the lungs, where the oxygen pressure is very high, around 100 millimeters of mercury, hemoglobin acts like a hoarder, just like myoglobin. It loads up to nearly 100% saturation.
It fills the truck completely.
Completely. But, and this is the entire secret to our survival, as it travels to the tissues where the oxygen pressure drops significantly, down to say 30 or 40 millimole in Hg, its personality flips. Its affinity for oxygen suddenly crashes.
And the S-curve shows that steep drop-off.
The curve dips steeply. It's like the truck arrives at the store and all the back doors fly open at once and it just dumps the cargo.
So it's high affinity in the lungs, low affinity in the tissues. That S-curve is what makes complex life possible. It connects the molecular biology to the environmental needs of the body.
It maximizes efficiency. It's a huge difference. If we use myoglobin for transport, we'd maybe deliver 5 or 7% of the oxygen we carried. With hemoglobin and its S-curve, we deliver about 40% of the oxygen we carry on every single pass through the body. It's a massive improvement.
Okay, before we get into the mechanics of how it does that, the magic behind the S, we have to talk about a true medical mystery that Harper covers so well, the kryptonite scenario, carbon monoxide poisoning.
This is a terrifying and beautiful example of molecular competition. We've been talking about affinity. Well, it turns out that a free heme group, just that iron ring floating alone, loves carbon monoxide. It binds CO 25,000 times stronger than it binds oxygen.
25,000 times.
25,000. The physics of the bond, the way the orbitals line up, it's just a much better fit for CO than for O2.
So if we didn't have some kind of defense mechanism, even the tiny amount of CO from a candle, or even the CO our own bodies produce as metabolic waste, it would suffocate us.
Essentially, yes. We would poison ourselves instantly. Our hemoglobin would become permanently clogged with CO. We wouldn't stand a chance if it were for a clever trick up its sleeve.
What is the trick?
It's a brilliant piece of molecular engineering called the distal histidine.
Okay, explain that using geometry. That sounds interesting.
All right. Imagine the binding site on the iron atom as a flat surface. Oxygen, O2, likes to bind at an angle. It comes in sort of slantwise, like a plane coming in for a landing on a runway.
All right.
Carbon monoxide, CO, on the other hand, prefers to bind perfectly perpendicular. It wants to stick straight up from the iron, like a flagpole. It wants to stand tall.
So CO wants to stand up straight, but O2 is happy to be bent.
Exactly. So the protein, the globin part that surrounds the heme, very cleverly positions an amino acid, a histidine residue, right over the binding site. It acts like a low ceiling in a room.
Ah, so the CO flagpole can't stand up straight.
It physically cannot.
Yeah.
The distal histidine gets in the way. It sterically hinders the COO. It forces the CO molecule to bend into an uncomfortable, strained angle if it wants to fit in there at all. And this strain significantly weakens the bond.
So it's like a bouncer at a club telling someone they're too tall to come in. It weakens the bond from 25,000 times stronger down to what?
Down to about 200 times stronger than oxygen.
200 is still a lot.
It is, which is exactly why carbon monoxide is still so dangerous. It's a silent killer because it still outcompetes oxygen for the seat on the hemoglobin bus. But that reduction from 25,000 down to 200 is just enough to allow us to survive in a world where CO exists. It gives oxygen a fighting chance.
It's really incredible to think that a single amino acid positioned just so, acting as a low ceiling, is what keeps us all alive.
It is a perfect example of structure dictating function.
Let's go back to that S-curve. How does hemoglobin switch personalities? How does it know to be a hoarder in the lungs and then a philanthropist in the muscles? This brings us to section 3, the dance of cooperativity.
Right. And this is the core concept of velocity. Allos means other, stereos means shape. It literally means that what happens at one spot on the protein affects a completely different spot, far away.
You called hemoglobin a tetramer, 4 subunits. How do they talk to each other across the molecule?
Think of the 4 subunits as, say, 4 anxious friends holding hands in a circle. When they are empty, no oxygen bound, they are in what we call the T state, P for tense.
Tense. What makes it tense? What does that feel like for the molecule?
It's physically rigid. It's stabilized by a whole network of salt bridges. These are ionic bonds between the different subunits. They're holding each other in a tight, constrained formation. In this T state, the heme pockets where oxygen binds are physically squeezed. They're constricted. They really don't want to pick up oxygen.
So binding that very first oxygen molecule is incredibly difficult.
It's a real struggle. The oxygen has to force its way into that tight pocket.
But once you force that first one in,
That's when the magic happens. Binding that first oxygen molecule forces a shape change in that one subunit. The iron atom literally gets pulled up into the plane of the heme ring. This movement pulls on the helix it's attached to, which then pulls on the neighbor. It's a domino effect.
and it breaks those salt bridges.
It snaps those salt bridges. The whole molecule shudders and undergoes this large-scale transition into a new shape, the R state. R for relaxed.
And in the relaxed state, what happens then?
The pockets pop open. They become much more accessible. Suddenly, the affinity for oxygen skyrockets. The second oxygen molecule binds very easily, the third binds even easier, and the fourth virtually hops on board with almost no effort.
I like the peer pressure metaphor that you sometimes see. The first subunit binds oxygen and then convinces all the others that it's the cool thing to do, so they all join the party.
Peer pressure is a great way to put it. This phenomenon is called positive cooperativity, and it works in reverse too. When hemoglobin gets to the tissues and loses just one oxygen molecule, the whole R state becomes unstable. It wants to snap back toward the T state, and in doing so, it literally ejects the remaining oxygen molecules.
So it really is an all-or-nothing system. It prevents the truck from just driving around half empty.
Exactly. It ensures that hemoglobin doesn't just trickle out oxygen one molecule at a time. It loads up fully, and then it dumps its cargo in a burst, exactly where it's needed most.
But that's the next big question. How does it know where it's needed? The body isn't uniform. My bicep during a workout needs way more oxygen than, say, my earlobe.
This is the genius of the Bohr effect. Hemoglobin is not a dumb truck. It listens to its environment.
What is it listening for? What's the signal?
It's listening for 2 things, acid and carbon dioxide. Think about a muscle that's working hard. It's burning glucose like crazy. It's producing metabolic exhaust. What is that exhaust?
It's CO2 and lactic acid, which is, well, acid, protons, H+.
Exactly. So the pH in that tissue drops, it becomes more acidic, and the CO2 levels go up.
And hemoglobin can somehow feel that change in acidity.
It can chemically sense it. Protons, plus and CO2 molecules, can bind to specific sites on the hemoglobin molecule, and crucially, these are not the heme sites where oxygen binds. They bind to other places on the amino acid chains.
So it's an allosteric effect.
A perfect example of velocity. And when these protons and CO2 molecules bind, they stabilize the T state.
The tense state. The state that has low affinity and hates holding on to oxygen.
The very same. So when a fully loaded hemoglobin molecule from the lungs enters an acidic, CO2-rich environment like that working muscle, the protons and CO2 from the muscle jump onto the hemoglobin. This locks it into the T state, and the T state can't hold oxygen well, so it releases it. It dumps its cargo.
That is just so elegant. The waste products of metabolism, the acid and CO2, are the very signal that tells the delivery truck, this is the spot, drop the package here.
It's a perfect physiological feedback loop. The harder the muscle works, the more acid it makes, and the more oxygen hemoglobin is forced to release right there. It's demand-driven delivery.
Now, there's one more regulator mentioned in both texts that's a bit less intuitive, 2.3 bisphosphoglycerate, or just BPG. Leininger often refers to this as the altitude adjuster.
Yes, BPG is a small, highly negatively charged molecule that's made in red blood cells. And it fits perfectly into the central cavity of the hemoglobin tetramer, but only when it's in the T state.
It doesn't fit in the R state.
No, in the R state, that central cavity collapses, so BPG acts like a wedge. It sits in that T state cavity and props it open, physically preventing it from easily switching to the high-affinity R state.
So it stabilizes the low affinity state, just like acid did.
Exactly. It lowers hemoglobin's overall affinity for oxygen.
But why would we want to have lower affinity? That feels counterintuitive.
This is the tricky part. Let's use the altitude example. Imagine you go from sea level to, say, Everest Base Camp. There's significantly less oxygen in the air. Your first instinct might be that you want your hemoglobin to have higher affinity to grab every last bit of oxygen you can breathe in.
That would absolutely be my instinct, make it stickier.
But actually, the bigger problem at high altitude isn't just loading oxygen in the lungs, it's unloading it in the tissues. If your hemoglobin holds onto the oxygen too tightly because of the low ambient pressure, your tissues will starve.
Ah, so you need to prioritize the delivery end of the equation.
You have to. So when you go to high altitude, over a couple of days, your body adapts by synthesizing more BPG. This BPG gets into the red blood cells, stabilizes the T state, and shifts the entire oxygen binding curve to the right. It lowers the affinity.
Which means you're better at letting go of the oxygen you have.
Exactly. It ensures that even though you might be picking up a little bit less in the lungs, you are much, much more efficient at dumping it in the tissues where it matters most. You're sacrificing a little bit of loading capacity for a huge gain in unloading efficiency.
Okay, so we have this incredible molecular machine. It breathes, it cooperates, it listens to pH and CO2, it adapts to altitude with BPG. It's a masterpiece. But machines break, and when we look at Harper, we see in vivid detail what happens when the structure fails. This brings us to section 4, clinical correlates.
And the most famous example of a structural failure leading to a functional catastrophe, and perhaps most tragic, is sickle cell anemia.
And this all comes down to a typo, a single letter in the genetic code leading to one wrong amino acid.
One single amino acid substitution on the beta chain of hemoglobin, at position number 6. Normally, at that position, there is a glutamate residue, GLU for short.
And what's glutamate like?
Glutamate is polar, it's negatively charged, and it absolutely loves being in water. It sits happily on the surface of the protein, interacting with the blood plasma. No problems at all.
And in sickle cell disease.
That glutamate is replaced by valine, VAL for short, and valine is the polar opposite. It's nonpolar, it's hydrophobic, it hates water. It's greasy.
So now, on the surface of this protein that's supposed to be dissolved in water, you have a sticky, greasy patch of valine just sitting there.
Right. A hydrophobic patch on a hydrophilic surface. And here is where the T state versus the R state comes back in a huge way. When hemoglobin is oxygenated in the R state, that greasy valine patch is sort of tucked away. It's not a major issue. The protein behaves more or less normally.
But when that hemoglobin releases its oxygen in the tissues,
It snaps into the T state. And in the T state, that sticky patch becomes exposed on the surface of the molecule.
and in the unbelievably crowded environment of a red blood cell.
That sticky patch on one hemoglobin molecule finds and locks into a complementary hydrophobic pocket on a neighboring hemoglobin molecule. They just click together like little Legos. Then a third one joins, and a fourth, and a fifth. They begin to polymerize.
They form long fibers inside the cell.
They form long, rigid helical fibers. They grow and grow until they are longer than the cell itself. These fibers physically distort and stretch the red blood cell from its normal flexible disc shape into that characteristic sickle or crescent shape.
And these sickled cells aren't soft and squishy anymore.
They're rigid. They're brittle. They act like logs trying to float down a river.
They get stuck in the small capillaries.
They get stuck and they block blood flow.
Mm.
This is what causes the excruciating pain crises and the organ damage seen in the disease. And because the cells are so rigid and misshapen, they're also fragile and break apart easily in the bloodstream. That's the anemia part of the name.
And notice the trigger you mentioned. It all happens in the T state, the deoxygenated state. So patients are most at risk for a crisis when they are exhausting themselves, or they have an infection, or they're at high altitude.
Any situation that lowers oxygen levels will accelerate the polymerization. It is a disease of protein conformational change triggered by a functional event.
It's just staggering that such a tiny change, one single amino acid out of hundreds, can cause such systemic devastation. But Harper also makes a point to mention the evolutionary trade-off here. Why hasn't natural selection just wiped this gene out? It seems so harmful.
Malaria. It's a fascinating and grim example of a balancing selection. The malaria parasite, Plasmodium falciparum, spends part of its life cycle living inside human red blood cells.
Right.
It turns out the parasite has a really hard time surviving and reproducing in cells that contain the sickling hemoglobin. The lower oxygen tension, the sickling itself, and the fragility of the cells all seem to disrupt the parasite's life cycle.
So if you're a carrier, if you have one bad gene and one good gene,
If you're heterozygous for the trait, you get significant protection against dying from malaria, but you don't have the severe, full-blown sickle cell anemia. It's a grim biological compromise that offers a survival advantage in regions of the world where malaria is endemic.
a terrible choice, but a choice that makes evolutionary sense. Okay, we spent a lot of time on hemoglobin, which lives inside the red blood cell, but I want to zoom out now. Let's look at the fluid the cells are floating in, the plasma, section 5, the plasma highway.
The plasma is an incredibly busy place. It's not just water and salt. It is packed with proteins, each with a critical job. And Harper gives us a wonderful tour of the major players.
And the undisputed heavyweight champion of them all is albumin.
Albumin, by a long shot. It makes up about 60% of all the protein in your plasma. It is the absolute workhorse of the blood.
I like to think of albumin as having two very distinct jobs. It's the sponge and it's the taxi.
That's a great analogy. Let's do the sponge first. This is all about something called oncotic pressure. We all remember osmosis from basic biology.
Yeah.
Water wants to move from an area of low solute concentration to high solute concentration.
Right, water follows the solutes.
Well, because there is so much albumin protein packed into the blood, it acts as a massive solute magnet. It creates a powerful osmotic force that pulls water from the surrounding tissues into the blood vessels, and just as importantly, keeps it there.
So without albumin, what happens?
The water doesn't stay in the pipes. It follows gravity. It leaks out of the capillaries and seeps into the tissues. This is called edema.
And you see this clinically.
You see it all the time. In severe liver disease, the liver can't make enough albumin, so patients get swollen legs and fluid in their abdomen. Or in severe malnutrition, like kwashiorkor, you see children with swollen bellies because there isn't enough protein in their diet to make the albumin needed to hold the water in their veins.
That's the sponge, a very powerful, very simple mechanical role. What about the taxi?
Albumin is also a fantastic carrier protein. It has a number of hydrophobic pockets on its surface, which makes it perfect for carrying all the things that hate water and can't dissolve well in the blood.
Like what?
Fatty acids, for one. They are shuttled from fat tissue to muscle on albumin. Bilirubin, the waste product from old red blood cells. A lot of calcium and steroid hormones. And, critically for medicine, a huge number of drugs.
So if you take a medication.
If you take something like ibuprofen or the blood thinner warfarin, chances are that albumin is the Uber driver carrying that drug through your bloodstream to its target tissue.
It's the universal transport vehicle. But it's not the only one. We talked about the dangers of iron earlier. We said free iron is toxic, so you can't just let it float around. How do we move it safely from, say, the gut to the bone marrow?
We use a dedicated high-security relay system. In the plasma, we have a protein called transferrin, which is like the armored car. It binds iron in its ferric state, plus 2 atoms at a time, extremely tightly to prevent it from causing those free radical reactions we talked about.
And when it gets to a cell that needs iron, what happens?
The cell has a receptor that grabs the transferrin, pulls the whole complex inside, and then the cell has machinery to safely release the iron.
And for long-term storage.
For storage inside the cells, we have ferritin. You can think of ferritin as the vault. It's this incredible hollow sphere of a protein that can hold thousands of iron atoms inside it in a safe, non-toxic, crystalline form.
It's a beautiful system. Now, Harper also mentions a surprising copper connection here with a protein called ceruloplasmin. What's that about?
This is a fascinating bit of biochemistry. Ceruloplasmin is a copper-containing protein, and one of its main jobs is actually to help load the iron onto the transferrin. It has an enzyme activity called peroxidase.
It oxidizes the iron so it can be loaded.
Exactly. It converts the Pb2+ to 5,2-PRO+, so that transferrin can bind it. So if you don't have enough functional ceruloplasmin, you can't handle iron properly. You could actually get anemic because you can't load the armored truck.
This is a key feature of Wilson disease, a genetic disorder where copper handling is broken, which leads to copper toxicity, but also problems with iron metabolism. It just shows how interconnected all these pathways are. I want to touch on one more group of plasma proteins from Harper that really illustrates the Medlock Holmes theme of defense and protection. The protease inhibitors, specifically alpha-1 antitrypsin.
AAT. This is the shield. Your body has immune cells called neutrophils. They are your frontline soldiers against bacteria. To do their job, they release a powerful enzyme called elastase, which is like a molecular scissors designed to chew up invaders.
But I'm guessing elastase isn't very picky about what it chews up.
It is not. It's dumb. It doesn't know the difference between a bacterium and your own delicate lung tissue, which is full of a protein called elastin.
So friendly fire is a big risk.
A huge risk. So to prevent this, your liver constantly pumps out alpha-1 antitrypsin, AAT, which circulates in the blood. Its only job is to find and inhibit elastase. It's a suicide inhibitor. It basically jumps on the grenade, it binds to elastase, and permanently shuts it down before it can do any damage to your lungs.
So what happens if you have a genetic deficiency and you don't make enough of this shield?
The elastase goes rogue. It's completely unchecked. It starts slowly digesting the elastic tissue in your lungs. Over years, this leads to emphysema, the destruction of the air sacs, even in people who have never smoked a day in their life.
But Harper does mention a very important smoking connection, too.
Yes, and this is the real tragedy of smoking from a biochemical perspective. Cigarette smoke contains powerful oxidizing agents. These chemicals get into your lungs and they chemically modify a single specific methionine residue on the alpha-1 antitrypsin protein.
And that modification breaks the shield.
It oxidizes the methionine, and that single change renders the inhibitor useless. It can't bind to elastase anymore. So if you smoke, you are actively chemically deactivating your body's own natural defense against lung destruction.
You're inviting the elastase to destroy your lungs.
You are unleashing the elastase on yourself. That is the primary mechanism for why smokers get emphysema. It's a powerful and direct biochemical assault.
That is a much more powerful way to understand it. It's not just smoke is bad. It's smoke breaks the specific protein molecule that is designed to protect your lungs.
Exactly. It's a targeted strike.
All right, let's move to our final section. We've talked about transport, we've talked about oxygen, storage, defense. Now let's talk about war. The immune arsenal, section 6.
Immunoglobulins, antibodies. This is where specificity, that concept we started with, reaches its absolute mind-boggling peak.
Leninger breaks down the structure so beautifully, we all have that image of the Y shape in our heads.
And the Y shape is absolutely critical to its function. It's composed of 4 polypeptide chains, 2 identical heavy chains and 2 identical light chains. But functionally, you should think of it as 2 different tools that have been welded together.
Okay, so let's break down that Y. You've got the stem at the bottom and the 2 arms at the top.
Right. The stem is called the FC2 domain. That officially stands for fragment crystallizable, but a much better way to remember it is as the handle. This part of the antibody is the constant region. It's the same for all antibodies of a certain class. This is the handle that your other immune cells, like macrophages, are designed to grab onto.
And the arms?
The arms are the Fab domains. That stands for fragment antigen binding. These are the hands, the very tips of the Y. And this is the variable region. This is where all the magic happens.
And when you say variable, you mean it?
I mean hypervariable. The amino acid sequences at the very tips of these arms are unique. Through an incredible process of genetic recombination, basically shuffling the DNA deck in your immune cells, your body can produce millions, maybe even billions of different shapes at the tips of these Ys.
And each one of those unique shapes is designed to grab one specific enemy.
One specific epitope. That's the technical term for the specific molecular feature on a virus or a bacterium that the antibody recognizes and binds to. And the binding is incredibly tight. The D-dollar is extremely low.
So the whole idea is you have this swarm of Y-shaped proteins. The tips, the Fab regions, grab onto the virus, and the stems, the FTC regions, stick out, waving a flag that says, hey, macrophage, come eat this, to the rest of the immune system.
Exactly. The process is called opsonization. It's flagging the invader for destruction. It's like putting a kick me sign on the back of a bacterium.
Now, Harper lists the different classes or isotypes of these antibodies.
Right. They're not all the same. IgG is the main one. It's the standard foot soldier in your blood. It's a monomer, just one Y. It's the workhorse of a mature immune response, and it's the only one that can cross the placenta to protect a fetus.
Then you have the first responder.
IgM. IgM is the first one on the scene of a new infection. It's huge. It's a pentamer. That means it's 5 Y-shaped antibodies all tied together at their stems. It looks like a snowflake or a sheriff's star. Because it has 10 hands, it is incredibly good at clumping bacteria together, a process called agglutination, early in an infection.
Then there's IgA.
IgA is the secretory antibody. It doesn't live so much in your blood as it does in your gut, your saliva, your tears, your mucus. It's the border patrol. It's the first line of defense at all your mucosal surfaces, stopping invaders before they can even get into your bloodstream.
And then there's the troublemaker, IgE.
IgE. This one is designed, we think, primarily to fight off parasitic worm infections. It has a special FDSE handle that binds to mast cells. When the Fab arms of IgE grab an antigen, it triggers that mast cell to degranulate, to explode with histamine and other inflammatory mediators.
Which is great if you have a parasitic worm you need to expel.
But terrible if the antigen you just inhaled is harmless ragweed pollen. That is an allergy. Anaphylactic shock is basically a massive, system-wide IgE response that is overreacting to a harmless stimulus.
One last distinction that always confuses students and that we hear about in medicine constantly, polyclonal versus monoclonal antibodies.
Okay, think of it like a police sketch of a suspect. A polyclonal response is what your body naturally produces. It means you have a whole team of different artists drawing the suspect from different angles. You have a whole mixture of different antibodies that all recognize the same virus, but they grab different parts, different epitopes of it.
That's a diverse attack.
A diverse, robust attack. Now, a monoclonal antibody is a clone army. You take one single B cell from the body that makes one specific, perfect antibody, the best one, and you clone it endlessly in the lab.
So you get a solution where every single antibody molecule is identical.
Identical, down to the last atom. This is absolutely crucial for modern medicine. All those biologic drugs that end in mab, like trastuzumab for breast cancer, are monoclonal antibodies. They are engineered magic bullets designed to hit one single molecular target with absolute precision and zero variation.
So we've traveled all the way from the microscopic twitch of a heme group
To the massive coordinated warfare of the immune system.
and the common thread through all of it.
The common thread is that biological function is physical interaction, its shape, its charge, its reversible binding, and above all, its context. Hemoglobin works because it changes its shape in the context of the lungs versus the tissues. Antibodies work because they have a specific shape for the context of a specific invader.
And when we look at disease, sickle cell, carbon monoxide poisoning, emphysema, it's rarely just that something is missing. It's so often that something is misbehaving, a protein is binding too tightly or too loosely, or it's clumping up when it shouldn't.
Medlock Holmes would conclude.
Yeah.
The suspect isn't absent from the crime scene. The suspect is acting suspiciously based on its geometry and its environment.
I love that. Okay, final thought for everyone. We've spent this whole time looking at proteins as these little molecular machines, motors, latches, pumps, shields.
We have.
Here's a provocation to leave you with. If these really are molecular machines that move and adapt and interact, could we, in the future, engineer them to build microscopic cities? Or if you look closely enough at the cell, is it already that city?
I think if you open Leninger to the protein function chapter or Harper to the chapter on hemoglobin and look at the space filling models, especially the simulations that show molecular crowding inside a cell, you'll see that it is indeed already a city, a bustling, chaotic, and beautifully organized city.
We'll leave you with that image. Go open the books. Look at the diagrams of that hemoglobin T to R transition. It really is a mechanical marvel.
Thanks for diving deep with us.
See you next time.